That viral idea that we're living in a computer simulation? It's captivating, but top minds argue it faces insurmountable challenges. Today, we're dissecting the powerful reasons why simulation theory is likely not the answer, and why reality might be exactly what it seems. Welcome back to our series looking into simulation theory. You've asked why simulation theory might be impossible or not real, and what the biggest arguments against it are. That's exactly what we're covering now. We'll explore the major scientific and philosophical challenges that make experts skeptical. We're presenting the critical view to give you a balanced understanding. In part 2, we heard compelling arguments for simulation. But how solid are they when faced with scrutiny? Are there fatal flaws in the simulation hypothesis that proponents often overlook? Understanding these counter-arguments is crucial for evaluating whether simulation theory is a plausible explanation for reality or just a fascinating modern myth. Let's systematically break down the 5 biggest reasons why we might not be living in a simulation. Challenge 1. Can you actually build it? Forget fancy code. We're talking raw processing power and energy. Let's talk scale. Imagine trying to track every single particle in the universe, maybe 10 to the power of 80 atoms. That's a 1 followed by 80 zeros across trillions of galaxies worth, all interacting constantly via complex quantum rules. The complexity is astronomical. There might be fundamental physical limits on computation. Think of principles like the Bekenstein bound, suggesting a maximum amount of information that can fit into any given region of space, or Bremerman's limit, which ties computation speed to available energy. You might literally run out of bits or juice to compute the universe. As physicist Michio Kaku bluntly suggested, the only computer likely powerful enough to simulate our universe is the universe itself. And quantum mechanics adds another layer of difficulty. Accurately simulating things like entanglement, where particles stay linked instantly over vast distances, seems incredibly hard, maybe impossible for standard computers. It's not just needing more speed, it might require a totally different kind of computation. The verdict? Simulating our universe down to the quantum level could demand more computational resources than might physically exist, potentially violating fundamental limits, even for hypothetical advanced simulators. It might just be physically impossible. So if it's scientifically slippery, does the theory at least simplify our view of reality? The next major argument pushes back hard on that idea. Challenge 2. Simulation theory is fascinating, but does it follow the basic rules of science? Specifically, can you test it? A core idea in science is falsifiability. A theory needs to make predictions that you could potentially prove wrong. Think of weather forecasts. You can check if they are right or wrong. Simulation theory has a tough time with this. Proponents might say, look for glitches, but what's a glitch versus just physics we haven't figured out yet? And if we find no glitches, well, they could just say it's a really good simulation. It can even explain away almost anything. Furthermore, many phenomena, sometimes speculatively pointed to as glitches or dark energy, actually have developing explanations within standard cosmology and physics, weakening the need to invoke simulation. Think about it. If a theory could never be proven wrong, no matter the evidence, would you consider it scientific? As astrophysicist David Kipling noted, a hypothesis that can explain any possible observation doesn't really predict anything specific. This makes it incredibly hard to distinguish from a philosophical idea or even an article of faith. It risks staying forever outside the reach of empirical testing. The verdict? Because it appears unfalsifiable, simulation theory lacks the testability that's fundamental to the scientific method. We currently have no reliable way to prove it right or wrong. Challenge 3. Is simulation theory an elegant simplification? Or just making things way more complicated than they need to be? Let's talk about Occam's razor. It's a principle suggesting we should generally prefer explanations that require fewer new assumptions or entities. Keep it simple, basically. Critics argue simulation theory fails this test dramatically. Think about what it asks us to accept on faith. Not just our universe, but 1. An unobserved base reality. 2. Unobserved simulators. 3. Their unobserved super technology. And 4. Their unknown reasons for simulating us. And that last point about motivations is key. Why assume hyper-advanced beings would even want to simulate 21st century Earth? That motivation itself is a huge guess. And what about explaining things like the universe's fine-tuning for life? Simulation could explain it. Designers set the dials. But it's not the only idea. Simpler explanations within physics exist, like the possibility of a multiverse combined with anthropic principle. We simply find ourselves in a universe whose laws allow us to exist. Plus, as physicist Frank Wilczek pointed out, the laws of our universe seem to have a lot of hidden complexity, intricate rules and symmetries that don't seem efficiently coded for a simple simulation outcome. If it was designed code, why make it so convoluted in places? What do you think? Does the fascinating nature of an idea justify adding extra layers of complexity and assumption? Or should we always favor the simplest explanation until proven otherwise? I'd be interested to hear your perspective in the comments below. Interesting perspectives there, no doubt. The verdict? Critics wield Occam's razor, arguing simulation theory adds multiple layers of unproven complexity and assumptions, including questionable motivations and potentially insufficient design, without strong justification, making standard physics the more scientifically straightforward approach. And speaking of adding layers, where does it end? That leads logically to the fourth major hurdle. Challenge 4. The simulators. The simulator's explanation sounds like an answer, until you ask the really awkward follow-up question. If we're in a simulation run by others, couldn't their reality also be a simulation? And the one above that? This leads to what philosophers call the infinite regress problem. Makes your head spin, right? It's like that old story. The world rests on a giant turtle, which rests on another turtle, which rests on, well, you get it. It's turtles all the way down. You never reach a final answer. This doesn't actually explain the ultimate origin of reality. And if you just say that there's a final, non-simulated base reality somewhere in the chain, well, the simulation hypothesis hasn't explained that reality. It's just kicked the can up the road. Physicist Frank Wilczek called this the embarrassing question. What is that base reality like? The verdict? Simulation hypothesis doesn't revolve around the fundamental mystery of existence. It risks creating an endless logical loop or merely displacing the ultimate question without answering it. That infinite loop is a head-scratcher, a purely logical puzzle. But the final challenge we'll discuss digs into something perhaps even more fundamental, the nature of experience itself. Challenge 5. The final, deepest hurdle. Can a computer, no matter how powerful, truly replicate subjective experience? Can you simulate the feeling of being alive? Simulation theory often banks on an idea called substrate independence. The consciousness isn't tied to flesh and blood. It could run on silicon chips just as well. But here's the massive caveat. We don't know if that's true. Explaining how physical matter creates the inner feeling of experience, the redness of red, the sting of sadness, the joy of laughter. Philosophers call this qualia. It's the famous hard problem of consciousness. It's one of science's biggest remaining mysteries. Even if a computer could perfectly mimic human behavior, responding intelligently and emotionally in ways we recognize, the core question remains. Would it have any genuine internal subjective awareness? Any feeling on the inside? Or would it just be an incredibly sophisticated puppet? Some leading thinkers, like neuroscientist Christoph Koch, argue consciousness might be fundamentally non-computable. Maybe it's tied to quantum effects in the brain, or specific biological properties computers can't mimic. And if consciousness can't be computed, then simulating beings like us, who generally feel and experience, might be fundamentally impossible. no matter how advanced the simulation technology. You could only create philosophical zombies, things that look conscious from the outside but have no inner life. The verdict? The theory rests heavily on the unproven and fiercely debated idea that consciousness is computable. If it isn't, the simulation hypothesis simply cannot apply to subjective beings like us. So let's pull these threads together, from fundamental limits on computation and scientific testability to philosophical hurdles like added complexity, logical paradoxes, and the profound mystery of consciousness itself. When you consider all these points together, they represent significant, perhaps overwhelming challenges for the simulation hypothesis. We've journeyed from the initial appeal of the theory to confronting the core scientific and philosophical counter-arguments head-on. And that powerful collection of counter-arguments is why, despite its undeniable fascination, many scientists and philosophers strongly suspect simulation theory is probably not real. The most plausible explanation, according to many experts, might still be the simplest one. We live in a complex, sometimes baffling, but fundamentally physical universe, operating under laws we're still striving to fully comprehend. Understanding these robust criticisms provides that crucial reality check and helps foster a more complete, nuanced perspective on this captivating modern idea. Want to unlock the power of AI? Our free newsletter gives you the tips, trends, AI news, and tools you need to succeed. Sign up with the link in the description below. Your journey doesn't stop here. Watch our next video right here and keep building your knowledge.